Earlier we looked at graphing the basic inverse trig functions, so now let's look at variations on that. So instead of just drawing y equals the inverse sine of x, how would we draw y equals 5 times the inverse sine of x on 3? So obviously we've got some transformations happening here. I think the easiest way for an inverse trig graph is to have a look at the domain and range first. Now, a regular inverse sine graph has a domain that goes x is in between -1 and 1. The difference here is we've got x on 3. So x on 3 will go in between -1 and 1, multiplied by everything by 3, and we get our new domain. So you can see we have that stretching effect that we saw with this type of transformation. X is now going in between -3 and 3. The range, when we deal with the range, we group it with the y value. It's the y value we're interested in. Now, y normally goes in between -pi on 2 and pi on 2. So this time, y divided by 5 is in between -pi on 2 and pi on 2. So our range becomes -5 pi on 2 to 5 pi on 2. And so we've also stretched it along the y-axis as well. Now, really, we just need to draw in the basic inverse sine graph. We just change the values on the endpoints of the domain and range. So on my axes, instead of going -1 to 1, I'm going -3 to 3. And on the y-axis, instead of going -pi on 2 to pi on 2, I'll go -5 pi on 2 to 5 pi on 2. Then I just draw in the basic inverse sine graph. And so there we have it. Y equals 5 times the inverse sine of x on 3. Those dilations are very easily handled. Now, y equals the inverse tan of the square root of 3 minus x squared. The domain for an inverse tan curve was all real x. But in this case, I can't substitute all real x in because of the square root. So that's what's caused me the problem. So what's under that square root sign still has to be a positive number, or 0. So 3 minus x squared is greater than or equal to 0. So I know the x value is going in between minus root 3 to root 3. Now what's going to happen with the range? Let's have a look at the endpoints of the domain. What happens at those points? So when x equals the square root of 3, the inverse tan of 0, inverse tan of 0 is 0. The same thing happens out at minus root 3 though, because we're squaring the x. Well, this makes sense. Inverse tan of root 3 minus x squared must end up being an even function, because whenever I substitute in negative x, I'm going to get the same as when I substitute in positive x, because we're squaring the x value. So I know it's going to be reflected in the y-axis. So it makes sense to now have a look at what happens at the y-axis. So when x equals 0, y equals the inverse tan of root 3, which we know to be pi on 3. My range, 0 to pi on 3. Let's draw that one up. And what we end up with is, well, it looks like it's not actually a semicircle, but it's got that sort of shape to it. The inverse sine of sine x. Well, we know that inverse sine of sine x, it's like saying the inverse sine of sine cancels, and we end up with x. So it must have something to do with the line y equals x. Let's look a little bit further. The domain, well, we know it's -1 to 1. So in this case, sine x has to go in between -1 and 1. Well, when does sine x go in between -1 and 1? It always does. If you think of the sine curve, it goes between -1 and 1. So the domain for this one is all real x. We could always substitute in a value for x here and get an answer. What's happening with the range? Well, it's still an inverse sine function. So the answers that we're getting out must be in between -pi on 2 and pi on 2. So how do we draw it? Well, there's my axes. I'll mark in every pi on 2, same as I would do for a sine curve. Now, we know it's based on y equals x, so I'll just draw that piece in of y equals x. But what happens from there? Well, what we can do is substitute in some other values to work it out. If I sub in pi, then I know that I'm going to get, well, sine of pi is 0, inverse sine of 0 is 0. So all of those multiples of pi will be x-intercepts. What we end up with is a zigzag. So it'll be zigzagging all the way along the x-axis. Sine of inverse sine of x, so the other way around. Now, our domain, this time we're substituting into the inverse sine function first. So the domain of this function must be the domain of the inverse sine function. I can only substitute in values in between -1 and 1, or when I substitute into this function, I won't get an answer for inverse sine x. And then we're going to say, what is the sine of those answers? So the range, let's have a look at the endpoints. X equals 1, I get the sine of inverse sine of 1, that is 1. -1, we get -1. 0, we get 0. So once again, it looks like we're getting y equals x, but we're going to stop at -1 and 1. So let's draw that in. Now this one won't zigzag though, because the domain of this function is in between -1 and 1. So we will stop our y equals x at -1 and 1. 17C is a handful of graphs there to try and draw.